Here we're going to look at Physical Chemistry Online Lab, Chemical Equilibrium and Kinetics. And we're going to give a brief overview of performing this project. Information can be found publicly at biopchem.education under Chem 343. And going to that website and going under project number 3, we'll see that looking at chemical equilibrium, we're going to look at tautomers, specifically of acetyl-acetone, which is tautomers between the ketone, the beta diketone, and enol forms of this. And background information as well as details about the online computational remote experimental data and error analysis is all provided within a handout of this material. And this is where students will often start, is reviewing this handout material and the subsequent references, noting that the primary objective is to use computational and experimental measurements to determine the thermodynamic equilibrium and kinetics of ketone enol tautomerization under various solvent and temperature conditions. And then it gives an overview of that. So starting with that, the background information, besides that, it's also good to do your own research. So going to somewhere like Scopus or Google Scholar, and after looking at the handout material, looking up some of the keywords to see not only the references provided in the handout, but what more modern references and other information you find. And so this is an example of doing a search here, and some of these first few things you can pull up and look at the articles directly, especially as an ASU student where you have access through the library to these journals. And reviewing some of this will reinforce some of the information and give you a good template for what your own report will end up looking like. This is looking specifically at some of the solvent dependence and how the solvent dipole moment changes the enol-ketone equilibrium. And you'll see NMR, proton NMR, where you can assign the ketone and enol resonances and then therefore get the concentration of each to give you an equilibrium constant, which is related to the free energy. And this is done for a series of different solvents, and then you can look at how those solvents affect the ketone-enol equilibrium under various models. So this is one example. An example of another where they do both computational, AM1 and density functional, and again they start pointing out the percent enol in different solvents and what that associated pKa is for the equilibrium between the two. So as you do that, you can start writing your introduction, providing those citations, and recording that information for your report. So that's why it's also recommended that you download the report template and at each stage start adding to your report and not saving it all to the end. After doing some of this literature search and kind of writing a first draft of your introduction with relevant references, you should have a good background information so that you're more prepared to get through the computational and experimental components. The computational components, it's recommended that you go to MolCalc, and here we can either use the chemical name or the SMILES. So if we look up the SMILES for acetyl-acetone on the wiki page, you should be able just to paste that in there and it will bring up, in this case, the ketone form. You can optimize its structure and then calculate its properties. You can also do this for the enol form. You could do it if you wanted to look at the various solvents to get what its polarity and various properties are so that you can do computation. We'll be looking temperature dependent, so the thermodynamic parameters are relevant, and then also we're interested in the polarity, the dipole moment of this, and its solvation energy properties in both the ketone and enol form of this. And so as we do these computations, you can save some of the results and tabulate some of the computational results obtained from this. Then after you do that section, you should have, again, you can produce a few preliminary figures and tables, as well as start writing your experimental materials and methods section for the computational component. Now that we've done some of that, it's nice to move on and look at some of the remote experimental components. And if we come here, we'll see we're going to access a live NMR spectrometer that has a bunch of samples put into the autosampler that can be run for remote experimental measurements. And this can be found using AnyDesk at the following address, and passwords are provided for students in Canvas. So going to AnyDesk and going to the Bruker 400, it'll often pull up. We're now pulling up a live view of that spectrometer, and it's running topspin and icon NMR to directly control the spectrometer. However, we can do everything from a web browser. And there's usually one open. It's usually a Chrome browser here. And we've given direct access to icon NMR and the live webcam. So that if we go here and, for example, call, oftentimes you need to reload it. So this is a live view picture of the 400. The samples are in this auto sampler here. If we zoom in on that auto sampler, we're going to where it moves the auto sampler and puts it into the spectrometer here so that we can get a live view of what we're doing. And then web icon here, it'll often time out and you re-log in for Chem 343. And we can run our sample here. So for example, and we give a list of the different acetylacetone in what solvents they're in and details about that here. You can schedule for time. So right now we're doing it on this time where we've scheduled time to show this, and students can sign up for time. This also provides some information about the samples in the spectrometer for your report. So we know that, for example, sample auto position number 3 is acetylacetone in benzene. So if we go here and click on experiment 3 and hit add, we can type the spentropy username, which is where it'll save the data. We can give it information. So project 3 video example. It's going to save it to a current Chem 343. You can increment experiment numbers. We're going to do a 1-scan proton on this. We can give it a file name. So I'm going to call this 2023-09. Today's the 18th. ACAC in benzene video test. We can tell it what solvent it's in. So this is in deuterated benzene. And we're going to run it the default temperature is 298, so we can add that experiment. It is now added there. We can now close this window if we want. So it's added. It hasn't started it, but if we click here and hit submit, it'll start that sample. We can go over to a live view of the spectrometer and see it putting in the sample as it moves over and puts it into the spectrometer. So it is moving over to position 3, and then we can watch it go to the sample and put it into the spectrometer and start it up. This sometimes happens where there's a delay between when, okay, so we can see here what sample it's gone to. It's gone to sample number 3, and it's the active one in there. We can go back here, and so that sample is now put in. And then here we can watch it as it goes through an auto tune and match. It'll lock the field, it'll shim it, acquire the data, process it, and then be done. We could start our next experiment right now if we wanted to. So we can, for example, add something here to experiment number 2 and run that one as well. We recently just ran this. So as that data is collecting, as long as you've typed the right spentropy name, it'll automatically get uploaded to there. So this is allowing us to remotely collect that data. And there's proton experiments you can run. You can run them at various temperatures, and you can run, there are these 9 different samples available for students to run so that they can collect data in different solvents and then also change the temperature of several of these. So you can queue up a bunch of experiments. You can look at a live view of everything and see what's going on. And we usually leave it here at the scheduler so that students can schedule time to queue up these experiments. Okay, once, so that gets us through going through collecting some of that data. Then you're going to want to process that to get the data and start processing it. So for this, the data is automatically getting saved to Spentropy under the ASU _Chem 343 account. So if we log into that, we can go to data, and as soon as it finishes running, it will show up here. This is one I ran earlier, so we can click, and if you click here, you can download the data and work it up on your own computer. You can also click on the spectra, and it'll take you directly to Equilibrium and open it up here, where now we can look at the data. We can go and integrate the data to get the areas of this. We can assign it. We can even, for example, have a chemical structure. Like, for example, here we know this is acetylacetone, so we can grab, for example, the ketone form of this. We can say we want to paste that in, and there's the ketone form. We can also grab the enol form, and there's the enol form in P2, and this is in P1, right? So now we have the chemical structures here. We have our data. We could integrate this. There's tutorials on how to integrate it, etc. Make plots of this. The first thing we want to do is to be able to assign this. We'll find that at 0 ppm, there's TMS. This is in acetone, so the acetone peak is right here. this is the TMS peak. All the other peaks are due to the acetyl-acetone. There are both methyls due to the ketone form, and then the methyls due to the enol form. Those are right here. One of these is the ketone form. One of them is the enol form of it. And then we have a methylene that is due to the ketone form, this methylene right here, and then a methine that's due to the 1 proton of the enol form. And then finally we have an acid proton, which is way out here. So that assigns each of those resonances in here. And we can then tabulate the chemical shift. We can integrate this so that we can tabulate the integrals of each of these. And so, for example, these are each 2 methyl groups, or a total of 6 protons. So the ratio of that would be a ratio of the ketone to the enol form and how much of each of those are in this sample at this temperature and in this solvent, which in this case is acetone. Once we're finished with this, you can export this, so you can make plots and export it. You can also predict the NMR spectrum of it. So, for example, the ketone form, we could predict the proton NMR of this form. It will put this in a separate one here. So it helps us assign through this prediction. So the prediction is there. The actual spectrum is there. And then we can see both of them together. So it shows us that this right here is the methylene, and it's close to the predicted value. This is right on the predicted methyl value. And then we can do that for the enol form as well. So once we have that, now we have the data. We can download it. We can also analyze it in NMRium and start getting the values we need for our data analysis. So that gets us to plotting some of that data, determining the equilibrium, doing standard data analysis. And then if at every step along the way you've added, when you did the background information, to your introduction, when you started doing the experiments, you added to your materials and methods. As you started doing your data analysis and making tables, you start adding those tables into your report. And by the time you get to this final step, you should already be 75% or so through finishing your report. So hopefully that gives you a brief overview of this and how to systematically get through this online project. Thank you.